Assalamualaikum warahmatullahi wabarakatuh. Selamat siang kepada para peserta seminar. Saya lihat sudah hadir salah satu pembicara kita, Bobby, salah satu alumni Teknik Metalurgi Untirta, yang hari ini akan jadi pembicara di awal ya. Nanti Prof. Paula akan jadi pembicara yang kedua mengingat perbedaan waktu ya. Gimana, Bobby? Sudah siap, Bob?
Oh iya, Pak. Langsung dimulai aja nih, Pak.
Ya, kita tunggu dulu lah. Masih ada 4 menit untuk ini. Mungkin Bobby disiapkan dulu segala halnya. Sambil nunggu ini ada 18, kurang lebih 18 partisipan. Mudah-mudahan dalam 4 menit ke depan kita udah bisa mulai. Ini sudah di-record, sudah live streaming juga sudah oke. Mungkin bagi peserta yang namanya masih Metalurgi Untirta, dimohon untuk mengubah dengan nama aslinya ya. Ya, saya rasa kita bisa mulai ya, Bob ya.
Oh iya, Pak. Benar, Pak. Ini ada filenya ternyata yang salah ini nih. Filenya nggak kebaca di MacBook. Bentar, Pak. Formatnya saya ganti dulu.
Itu bukan opa itu.
Ya, sambil menunggu Bobby menyiapkan skill satunya, saya hanya menginformasikan bahwa kami sudah men-share acara untuk tanggal 23 November ya. Insya Allah ada 3 pembicara, satu dari Teknik Material ITB, kedua dari Tampere University di Finlandia, dan yang ketiga saya lagi menunggu kepastiannya, itu adalah atase bidang sains dan teknologi dari Kedutaan Besar Perancis di Indonesia. Jadi silakan lihat di chat dan ada langsung bisa diklik link registrasinya. Gimana, Bob?
Iya, Pak.
Sudah siap?
Siap.
Oke. Baik, kita mulai saja. Jadi hari ini kita kedatangan salah satu alumni Teknik Metalurgi Untirta ya. Angkatan berapa, Bob?
Saya angkatan 2011, Pak.
2011 ya?
Iya.
Jadi CV singkat, profil singkat Bobby, itu Bobby Aditya Darmawan. Saat ini tinggal di Korea Selatan ya. Pendidikannya S1 dari Teknik Metalurgi Untirta, masuk 2011. Lalu pernah menjadi ikut sebagai student exchange, pertukaran pelajar dengan Global Korean Scholarship ke Chonam National University di Korea Selatan tahun 2015. Lalu akhirnya mengambil S2 di bidang Material Science dan Engineering di Chonam National University juga, dan mulai 2018 menempuh pendidikan PhD di Mechanical Engineering Chonam National University South Korea. Dan mungkin untuk risetnya Bobby bekerja di Nanobiomaterials Team ya, di Korea Institute of Medical Microrobotics atau KIMIRO sebagai graduate research assistant. Hari ini Bobby akan memaparkan tentang perkembangan robotik ya. Mudah-mudahan bisa menambah wawasan pengetahuan kita semua. Oke, silakan Bobby untuk memulai presentasinya.
Ya, terima kasih Pak Adit. Saya share screen dulu ya. Oke, terima kasih Pak Adit atas perkenalannya. Sekali lagi perkenalkan, nama saya Bobby Aditya Darmawan. Saat ini sedang lanjut S3 di jurusan Mechanical Engineering di Chonam National University. Sebelumnya lanjut S2 di kampus yang sama tapi di jurusan Material Science and Engineering. Jadi beda jurusan tapi sekarang tetap fokus ke biomaterial. Selain jadi mahasiswa, saya juga researcher di Korea Institute of Medical Microrobotics, tepatnya di tim nanobiomaterial. Jadi outline presentasi saya hari ini, pertama itu akan membahas tentang medical microrobot, kemudian magnetic control microrobots, Kemudian yang di part ketiga, saya akan membahas tentang paper terakhir saya, tentang self-folded helical microrobot for precise targeting and control drug delivery. Kemudian yang terakhir, kita akan membahas tentang future and challenge microrobot ini. Oke, jadi pertama kita akan membahas dulu ya tentang medical microrobots, apa itu microrobots dan cara membuatnya dan cara mengkontrolnya. Oke, sebelum kita mulai presentasi, sebelum mulai ke topik bahasannya, saya akan nampilin dulu video tentang maybe history of microrobot. Jadi ini film tentang microrobot, keluar tahun 1966. Jadi ini sebelum saya lahir juga. Judulnya Fantastic Voyage. Jadi mungkin buat bayangannya aja ya. Ini bukan microrobot tapi sebagai inspirasi dimulainya microrobot. Oke, kita mulai aja videonya. Ya mungkin cukup lah ya. Udah kebayang mungkin tentang microrobot itu sendiri. Jadi kalau dilihat dari film ini, kita tahu bahwa dia itu mengecilkan sebuah spaceship buat dimasukin ke dalam tubuh dan melakukan something di dalam tubuh itu sendiri kan. Kita anggaplah sebagai invasive surgery. Oke, jadi dari film ini kita bisa tarik kesimpulan bahwa microrobot itu beda banget sama robot yang kita ketahui. Jadi ini salah satu contohnya adalah humanoid. Jadi itu bukan, jadi ini beda banget ya. Dari segi ukuran dan juga dari lain-lain. Oke, jadi secara definisi itu medical microrobot adalah small device from millimeter to micrometer in size, which can travel in human body and perform specific tasks. Jadi spesifik testnya itu salah satunya adalah drug delivery atau gene delivery atau invasive surgery. Dan microrobot itu pertama harus biocompatible. Kenapa biocompatible? Karena microrobot ini kan kita masukin ke dalam tubuh. Jadi intinya harus biocompatible dan tidak toksik ke jaringan di dalam tubuh. Yang kedua, controllable. Karena microrobot ini kita masukin ke dalam tubuh dan enggak otomatis. Jadi harus bisa dikontrol, entah itu dari kontrol direction-nya atau kontrol misalkan fungsinya buat seperti contohnya adalah intravascular therapeutic microbot ini. Jadi misalkan harus gerakannya dikontrol atau dan sejenisnya lah ya. Terus yang ketiga adalah biodegradable. Jadi saya kasih tanda bintang ini biodegradable karena materialnya ini walaupun nggak biodegradable, asal dia bisa ditarik kembali, itu juga nggak apa-apa. Sebagai contoh, misalkan misalkan kita punya microrobot dan ada di dalam lambung. Karena lambung ini kan sebetulnya jaringannya nggak terlalu how say complicated gitu. Jadi kayak misalkan dari kerongkongan dan masuk. Jadi kan kita kontrolnya juga nggak terlalu ribet karena dari mulut tinggal langsung ke lambungnya. Itu asalkan bisa ditarik kembali, maksudnya bisa dikeluarin kembali, itu nggak mesti biodegradable. Tapi kalau misalkan di dalam kidney atau dalam pankreas itu kan jaringannya udah dalam tubuh banget, dan bagusnya itu harus biodegradable. Ini salah satunya adalah intravascular therapeutic microrobot. Ini salah satu microrobot yang dikembangin di lab saya. Kemudian di kanan ini adalah helical microrobots yang saya buat. Jadi bentuknya itu helical, dan bisa dilihat motion-nya itu dia ngebentuk helical motion. Oke, selanjutnya itu adalah perkembangan dari microrobot itu sendiri. Mungkin ini awalnya dari tahun 1950-an, itu muncul tablet dan kapsul, kemudian juga ada Feynman's lecture, itu tentang nanomaterials, kemudian tahun 60-an tadi filmnya itu, Fantastic Voyage, jadi menginspirasi researcher buat make it small device buat ke dalam tubuh. Kemudian lanjut tahun 2000-an itu baru mulai muncul kontrol bakteri ya, jadi dia dikontrol secara magnetik. Kemudian juga tahun 90-an itu muncul doxorubicin, yaitu anti-cancer yang ter-approve sama FDA, dan sekitar tahun 2010-an itu baru muncul BioInspire helical microrobot. Dan juga sekarang ini banyak banget jenis-jenis robotnya, jadi dari ukurannya juga udah menjadi nano, jadi nggak micro lagi. Oke. Kemudian aplikasinya. Jadi microrobot ini sebenarnya aplikasinya banyak banget. Salah satu contohnya itu adalah cell manipulation atau blood clot removal, wound healing, drug delivery, cell delivery, non-invasive surgery, atau gene delivery, dan lain-lain. Ini salah satu contohnya adalah dia itu deliver sperm cells buat proses fertilisasi menggunakan magnetic microhelix. Atau kemudian ini adalah buat clot removal, ini adalah scaffold buat membantu proses regeneration cell-nya. Atau ini ada stand-nya juga, jadi yang bisa dikontrol dari segi shape morphing-nya. Untuk microrobot sendiri, salah satu material yang digunakannya adalah biomaterial. Sebenarnya bukan salah satunya, adalah satu-satunya material yang digunakan adalah biomaterial, karena biomaterial ini kan luas banget cakupannya. Oke, jadi biomaterial sendiri mungkin udah di Indonesia udah banyak juga perkembangannya ya. Jadi bisa diketahui bahwa definisi dari biomaterial itu adalah material organik ataupun inorganic to replace a loss or damaged tissue. Jadi buat mengganti jaringan yang rusak atau hilang. Dan biomaterial ini pastinya harus memiliki mechanical property yang bagus, chemical property yang bagus, dan juga biological property-nya harus bagus. Jadi ya biocompatible lah ya intinya. Dan untuk microrobot sendiri, Material yang digunakannya itu sangat tergantung dari aplikasinya dan juga dari robot size-nya. Sebagai contohnya, misalkan kita kembali lagi ke robot buat di dalam lambung. Karena di dalam lambung itu nggak mesti nano atau ya ukuran in 1 mm juga bisa lah ya. Jadi kita bisa menggunakannya juga misalnya kayak FDA approved polymer atau mostly polymer sih yang digunakannya ini. Terus kita bisa menggunakan 3D printer, kemudian dibentuk micro robotnya, kemudian baru bisa digunakan. Mungkin pertanyaan selanjutnya adalah how to make micro robots. Jadi sebenarnya pembuatan micro robot itu banyak banget caranya, dan salah satunya ini adalah direct laser writing. Ini merupakan 3D printer, tapi buat skala nano dan juga puluhan mikro. Jadi ini tuh kecil dan juga presisi banget. Tapi salah satu kekurangannya dari alat ini, dia itu pertama mahal banget, dan kedua gampang rusak dan sensitif banget. Terus bisa juga menggunakan 3D printer atau Electron Deposition atau 2D lithography. Jadi kalau untuk 2D lithography ini dia membentuk bukan 3D ya, jadi kayak semacam 2 dimensional micro robot itu. Atau bisa juga menggunakan emulsion. Jadi emulsion ini sebenarnya agak beda juga dengan litografi. Jadi dia menggunakan water in oil emulsion atau oil water emulsion dan sebagainya. Kemudian bagaimana sih si microbot ini bergerak? Mungkin seperti yang kita ketahui sendiri bahwa di dalam tubuh manusia itu water levelnya sekitar 70%. Ya di atas 70% lah ya. Jadi researcher itu dia terinspirasi dari microorganism kayak bakteria. Jadi bakteri ini dia kan bergerak menggunakan silia atau flagellanya. Jadi walaupun dia tuh kecil banget, tapi dia bisa bergerak sendiri, gitu ya. Jadi kebanyakan dia itu researcher itu mimicking, jadi mengikuti pergerakan si microorganismnya ini. Terus cara tracking microrobotnya. Jadi setelah dimasukin ke dalam tubuh, gimana kita trackingnya kan? Itu sebuah pertanyaan selanjutnya. Jadi trackingnya ini ada beberapa cara. Pertama adalah optical tracking, magnetic tracking, itu juga bisa kayak MRI, X-ray tracking, dan juga ultrasound. Jadi di lab saya itu kita punya X-ray tracking dan juga ultrasound. Cuma di sini saya akan tampilin aja ya X-ray trackingnya. Ini adalah skematik X-ray tracking di lab saya. Pertama kita punya EMS system, electromagnetic actuation system, dan di atasnya itu diinstal X-ray tube-nya dan juga harusnya di samping juga ada juga. Jadi kayak double X-ray tube gitu buat proses imaging-nya. Dan ini adalah proses imaging menggunakan X-ray. Jadi bentuk-bentuk bulat ini merupakan microrobot. Jadi karena bentuknya banyak banget ya. Jadi ini saya cuma ambil fotonya doang buat ngecek image quality-nya. Kemudian tipe microrobot. Jadi sebetulnya tipe microrobot ini tuh gimana ya? Ada yang menggunakan bentuknya sebagai tipenya atau cara pembuatannya atau surface functionalization-nya. Jadi tipenya itu tergantung dari presenternya sendiri ya. Cuma di sini saya akan present I will talk about microrobot depending on propulsion. Jadi how it move. Jadi bagaimana pergerakannya dia sendiri? Ini tuh sebenarnya ada 6. Yang pertama ada magnetic, light, electric, ultrasound, hybrid, dan juga ada chemical. Jadi hybrid ini dia juga bisa double ya, entah itu dengan chemical atau bisa juga dengan ultrasound, dan jadi kayak double gitu. Tapi untuk selanjutnya, karena fokus saya itu adalah magnetically control microbot, jadi di sini saya cuma akan bahas tentang magnetic control-nya aja. Oke. Dan selanjutnya kita akan masuk ke part kedua, yaitu tentang magnetic control microrobots. Oke. Ini kenapa sih kita pakai magnetik ini? Salah satu keunggulannya itu adalah dia biocompatible. Jadi dia walaupun menggunakan magnetik ini nggak merusak sel di dalam tubuh. Kemudian easy to control dibanding propulsion yang lain, magnetik ini lebih easy to control, dan dia juga penetrate in most material, including the body. Jadi berdasarkan paper yang saya baca itu dia bisa nembus sekitar 2 cm atau 3 sentian gitu. Jadi walaupun di dalam tubuh dia masih bisa melakukan pergerakan. Di dalam tubuh maksudnya bisa tetap dikontrol. Oke. Kemudian ini sebagai ilustrasinya aja ya. Ini yang hitam-hitam ini dia merupakan contoh adalah microrobot. Kita di sini ada magnet. Jadi ya tinggal dia bergerak mengikuti si magnetnya aja kan. Oke, kemudian ini adalah contohnya. Ini microrobot yang saya buat, kemudian dideketin dengan magnet. Jadi dia cuma ngikutin magnetnya aja. Itu kalau pakai magnet ya. Ya sebagai contohnya kalau ada magnet di kiri dia juga ngikutin ke kiri. Ini buat lebih advance-nya lagi menggunakan electromagnetic coils. Karena kan kalau kita cuma pakai magnet itu controllability-nya kurang bagus, makanya kita menggunakan electromagnetic coils. Jadi buat bergerak untuk mengontrol motion-nya juga, dan juga untuk direction-nya juga lebih gampang. Dan pertanyaannya ini adalah butuh berapa electromagnetic coils buat bergerak ke misalnya kayak 3 degree of freedom atau 5 degree of freedom. Itu tuh nanti tergantung lagi dengan si magnetic propulsion-nya ini. Jadi sebetulnya kalau untuk butuh berapa coils untuk mengkontrol microbot ini sebenarnya agak dengan harus benar-benar kalkulasi. Cuma ini bukan bidang saya, jadi saya juga nggak bisa ngejelasin dengan jelas. Cuma intinya ini butuh kalkulasi buat menentukan jumlah coils yang dibutuhkan buat mengontrol si microrobot. Kalau di lab saya sendiri itu kita punya 8, jadi di atas 4 sama di bawah 4. Dan kayak mengelilingi si workspace-nya itu. Dan untuk propulsion-nya sendiri, itu pertama kita harus mengetahui si magnetic force-nya sama magnetic torque-nya. Ini adalah basic physics ya. Jadi ini sangat penting buat mengetahui pergerakannya si microrobot ini. Kemudian ini adalah electromagnetic actuation system yang ada di lab saya. Di sini ini adalah coils-nya. Jadi seperti yang saya bilang sebelumnya, jadi ada 4 di bawah sama 4 di atas, dan ini adalah workspace-nya. Kemudian kameranya diinstal di atas di atas workspace-nya. Jadi sebagai ganti kamera kita juga bisa mengganti sebagai X-ray-nya ya. Kalau misalkan mau menggunakan X-ray buat imaging-nya. Dan ini adalah salah satu contohnya, yaitu jadi misalkan dari di sini adalah posisi awalnya untuk ke posisi B. Jadi menggunakan IMS system ini, dia bergerak dari sini terus ke sini, ke yang B, bagian B-nya. Kemudian ini saya akan mengambil salah satu contoh. Ini macrophage based microrobot, salah satu microrobot yang dikembangkan di lab saya. Itu dia menggunakan biodegradable material, PLGA, dan juga magnetic microparticle dan juga anti-cancernya. Kemudian menggunakan nukleus anti-cancer, dan juga di delivery buat ke dalam tumor, dan karena itu dia akan rilis. Jadi dikontrol dengan efek, karena ada magnetic nanoparticle di sini, jadi dia bisa dikontrol secara magnet dan juga bisa di delivery. Dan karena ini adalah biodegradable, jadi nggak mesti khawatir, mesti di retrieve lagi, mesti ditarik lagi. Ini juga, ini merupakan salah satu bentuknya. Jadi kayak gini, bentuk macrophage-nya. Ini adalah si partikel magnetnya atau partikelnya, sekitar 6 nanometer. Jadi jadi proses awalnya itu yang pertama kita harus ngambil datanya ya, kayak semi-DS-nya, kemudian cek magnetic property-nya, dan setelah cek magnetic property-nya ini, misalkan kayak ini dia udah kedetek sebagai super paramagnetic, kemudian baru bisa digunakan menggunakan EMA system. Dan salah satu bentuk lainnya adalah soft gripper. Jadi ini paper senior saya tahun 2016. Dia menggunakan stimuli responsive material, yaitu HIMA. Jadi dia pH stimuli, kemudian double layer dengan PHDA with the magnetic nanoparticles. Jadi karena dia itu adalah stimuli responsive dengan pH, ketika didekatkan dengan sel cancer, karena sel cancer itu dia pH-nya sekitar 2 atau 3, jadi dia bisa melepas si drug-nya. Jadi ini sebagai cargo delivery ya. Jadi bukan atau drug atau cargo delivery. Ini salah satu videonya. Jadi dia bisa proses folding and unfolding berdasarkan pH sekitarnya. Kemudian ini dibagi menjadi low pH dan juga high pH. Jadi diarahkan ke low pH-nya ini. Kemudian dengan unfolding motion-nya, dia juga melepas si drugs-nya itu. Oke. Kemudian ini salah satu contoh lain, yaitu adalah scaffold. Jadi scaffold ini dia digunakan buat regeneration of cartilage menggunakan si mesenchymical stem cell, dan dibuatnya ini juga menggunakan proses emulsion, kemudian dengan EMA system di delivery ke damage cartilage-nya ini, kemudian dengan proses fixation-nya ini. Jadi fixation ini karena dia butuh proses buat regenerasi, jadi bagusnya itu adalah fixation, biar si microrobot ini nggak kemana-mana, jadi tetap di posisi yang sama. Ini di sini adalah hasil SEM-nya dan juga hasil IDS-nya. Dan ini mungkin might be disturbing for some people, karena ini adalah proses in vivo-nya. Jadi menggunakan rabbit, menggunakan kelinci. Ini percobaannya dari sini ada EMA sistemnya dan juga dia di tibianya. Rabbit. Jadi ini menggunakan EMA sistem, dia akan tetap stay di sini. Kemudian tanpa EMA sistem dia akan kemana-mana. Maksudnya nggak stay di tempat yang sama. Ini kemudian ini contoh terakhir ya. Ini helical microrobot seperti yang salah sebut contoh sebelumnya tadi ada di awal, bagian awal. Jadi ini adalah helical microrobot, ukurannya sangat kecil. Dia itu dibuat menggunakan direct laser writing. Ini kayaknya sekitar berapa nano size gitu. Sekitar 15 nano, kalau dilihat dari sini, 15 nanometer, 15 micrometer size-nya. Di sini filenya bisa kebuka. Jadi dia ini inti prosesnya adalah buat delivery sperm cell ke sel telur buat membantu proses fertilisasi. Ini video buat bagaimana dia itu mengambil si spermnya, kemudian diarahkan juga. Ini juga dia menggunakan IMA system ya. Jadi bisa tadi sebelumnya ditangkap, kemudian terakhirnya juga bisa dilepas. Ini menggunakan helical motion. Kemudian kita bahas ke part 3, yaitu self-folded helical microrobots for precise targeting and control drug delivery. Ini adalah paper saya, baru publish Agustus lalu. Oke, jadi background dari riset ini pertama adalah untuk precise delivery, terus control drug release, faster movement, dan juga simple fabrication. Jadi ini adalah objektif. Jadi tujuan dari riset ini. Dan riset ini menggunakan dua material. Itu adalah FDA-approved polymer. Ini adalah IDN 400. Jadi ini adalah commercial material dari Germany. Kemudian NdFeB magnetic microparticles. Kemudian di mix selama 30 menit dengan 2000 rpm menjadi composite resin. Ini adalah konsepnya. Jadi menggunakan IMA system digunakan buat delivery microrobotnya, misalkan ke bagian si tumornya ini, ke cancer cell-nya ini, dan menggunakan high intensity focus ultrasound itu buat men-trigger drug release-nya. Jadi dengan adanya si ultrasonic ini, dia itu untuk melepas si drug yang nempel di microrobotnya. Dan cara membuat microrobotnya ini, pertama kita harus menyiapkan microchamber. Jadi microchamber ini dia itu adalah cover glass dan slide glass. Jadi ada dua glass yang tipis banget. Kemudian di tengah-tengahnya ditempelin double side tape. Jadi karena ada double side tape ini, dia punya thickness. Nah, thickness-nya itu merupakan thickness microbot yang akan kita buat. Sebagai contoh, misalkan kita mau buat yang 50 micrometer, jadi tempelin tape-nya yang 50 micrometer. Dan kemudian, setelah kita punya composite resin yang tadi, kita masukin composite resinnya ke sini, menggunakan capillary force, sampai dia full, dan kita arahkan ke optical system ini. Ini yang tadi saya bahas adalah litografi. Ini di sebelah kanannya adalah schematic prosesnya. Jadi ungu ini adalah ultraviolet, dan ini adalah lensnya. Dan ini chamber yang kita buat. Dan resin ini ada di tengah-tengah. Jadi di antara jadi resin itu, fotoresistnya itu masuk ke dalam sini. Kemudian dengan proses selama 6 detik, jadi langsung menggunakan UV, langsung curing the material selama 6 detik, dan menggunakan self-folding, kita bisa membuat material dari awalnya itu adalah 2D dimension menjadi 3D dimension. Jadi dari awalnya cuma membrane tipis gini menjadi helical. Jadi menjadi 3D helical. Dan salah satu keunikan material ini, dia selain bisa folding, jadi awalnya ini adalah folding ya, dia juga bisa unfolding. Jadi kayak shape memori polymer, tapi ini bukan, karena ini commercial material ya, jadi kurang tahu entah dia SMP atau bukan. Cuma intinya material ini dia memiliki reversibility yang bagus. Dan unfolding ini dia menggunakan etanol, maksudnya di dalam etanol ini dia menjadi folding, kemudian menggunakan DMSO atau ethyl acetate, dia menjadi unfolding. Cuma untuk unfolding and folding ini masih belum cukup, maksudnya masih butuh bahasan buat dijadikan medical application, karena DMSO itu terlalu toxic di dalam tubuh. Cuma intinya kita cuma menggunakan si folding shape-nya ini buat proses selanjutnya. Kemudian ini adalah hasil SEM EDS-nya, hasil SEM dan EDS-nya. Jadi kita lihat bentuknya ini adalah helical, kemudian dengan EDS kita dapat karbon itu dari si polimernya, kemudian ND dan Fe-nya itu dari ND-FeB, dan bisa kita lihat di sini juga, itu di sini ada partikel-partikel kecil, ini adalah si ND-FeB-nya ini, jadi kita bisa simpulkan bahwa si ND-FeB, magnetic microparticles, itu distributed uniformly inside the microrobot. Jadi inside the structure-nya ini sampai ke belakang sini itu ada magnetic microparticles semua. Kemudian kita cek lagi menggunakan VSM, Vibrating Sample Magnetometer, buat mengecek magnetic property-nya. Jadi di sini kita punya value MMPs-nya hampir 2 kali lipat ya, karena di microrobot ini kita kan combine dengan polymer, sehingga value-nya beda. Jadi value-nya itu depends on the concentration of MMPs. Kemudian adalah itu control-nya, jadi magnetic karena adanya si ND-FeB, sehingga kita bisa mengontrol secara magnetik. Ini adalah electromagnetic actuation system skematiknya, seperti sama yang kayak awal-awalnya ya. Dan untuk material di sini, jadi karena si magnetic partikelnya belum line, jadi direction itu masih random, sehingga harus di align untuk memiliki direction yang sama, kemudian dengan menggunakan magnetic proportion principles, kita bisa dapat kayak di sini dia adalah body rotation-nya aja, jadi kayak cuma muter-muter di tempat yang sama, tanpa kedepanin, maksudnya tanpa diarahkan ke depan. Kemudian ini adalah prosesnya untuk targetingnya, precise targeting. Ini speed-nya dicepetin ya. Oke. Kemudian setelah kita dapetin tadi bahwa microrobot ini dia bisa dikontrol secara magnetik, kemudian kita akan bahas tentang drug release-nya. Jadi ini pertama adalah coating prosesnya. Jadi microrobot ini sebelum di coating dengan anti-cancer doxorubicin itu menggunakan PDA, polydopamine. Jadi ini buat surface functionalization. Intinya mungkin PDA ini ilustrasinya sebagai lem gitu ya. Jadi sebagai glue buat nempelin si doxnya, biar doxnya ini doxorubicin nempel di microrobot. Kemudian setelah di coating, kita harus mengecek juga kan, entah itu doxorobicinnya nempel atau enggak. Soalnya ini kan pertama microrobot itu kecil dan warnanya itu hitam. Ketika dicampur dengan doxorubicin, itu doxorobicinnya nggak akan kelihatan secara dengan mata. Jadi harus dicek absorbansinya dan juga dengan confocal image. Jadi bisa dicek dengan dua metode ini. Entah itu doxorobicinnya attach atau enggak. Setelah kita confirm itu attach, kemudian ini adalah kemudian ini ada ini di sebelah kiri itu ada drug coated microrobot, kemudian menggunakan HIFU, high intensity focus ultrasound. Dia ini skematiknya ya. Jadi dari awalnya attach ke substrate-nya ini, kemudian setelah proses HIFU, dia akan terlepas. Jadi dari misalkan udah ditargeting, setelah targeting ke tumor area-nya, kemudian dilepas dan proses apoptosis begin. Jadi proses membunuh si cancer cell-nya itu. Ini kemudian adalah hasil biocompatibilitasnya. Itu walaupun kita menggunakan 1, 5, atau 10 microrobot, itu microrobotnya tetap biocompatible, jadi nggak membunuh sel. Kemudian kita tes drug release menggunakan pH 7 dan juga pH 5 tanpa HIFU stimuli. Kira-kira setelah 25 jam, setelah 1 hari, itu cuma 50-an% yang rilis di pH 5, kemudian 30%-an di pH 7. Tapi menggunakan HIFU, ini di merah, ini merupakan HIFU, the high intensity focus ultrasound. Ini setelah 60 second, hampir 100% drug-nya itu rilis. Dan yang merah, gray ini merupakan drug release menggunakan metode lain, yaitu NIR light. Cuman NIR light ini dia jauh lebih slow, jauh lebih lama proses rilisnya dibanding si HIFU ini, karena dia kayak simultaneously release the drugs. Dan dicek juga effectivity-nya. Jadi di sini adalah cell viability buat di cancer cell-nya. Jadi cell drug effectivity against the cancer cell. Ini adalah cell only, jadi tanpa microrobotnya. Ini microrobotnya doang. Jadi kita lihat ini adalah masih tinggi ya, sekitar. Jadi kan microrobot ini biocompatible, jadi dia nggak ngebunuh si sel cancernya. Tapi dengan menggunakan microrobot plus dox-nya, jadi tanpa ada stimuli, natural release, itu sekitar 60% dia ngebunuh si cancer cell-nya. Dan ini drug coated microrobot menggunakan HIFU itu sekitar 20, hampir 30% dia cell viability-nya. Jadi hampir 30%, intinya 70% dia ngebunuh si cancernya. Jadi cell viability-nya adalah berbanding kebalik ya. Jadi kalau misalkan dia lebih ke bawah sini, berarti dia ngebunuh banyak selnya. Dan ini diambil setelah 1 hari. Ini adalah live dead cells imaging. Jadi bisa lihat ini si dox loaded microrobot plus HIFU. Ini tuh merah semuanya, hampir merah semua. Ini merah berarti dia matinya. Kemudian terakhir itu adalah feature and challenge. Jadi ini saya tampilin global robotic market. Sebenarnya ini nggak spesifik ke microrobot, tapi seperti yang mungkin kita tahu bahwa kedepannya robot pasti akan banyak banget digunakan di dunia. Dan ini juga salah satu marketnya tahun 2025 itu sekitar 66,9 billion US dollar. Jadi dengan perkembangan si robotik ini, pastinya microrobot juga akan berkembang. Seperti misalnya kayak belakangan ini juga banyak banget riset tentang microrobot itu sendiri. Dan challenge-nya sendiri, ini tetap biocompatibility-nya ya. Jadi walaupun microbot itu punya biocompatibility yang bagus, tapi karena kebanyakan itu masih sebatas proof of concept. Jadi belum ke in vivo. Jadi intinya kita harus ngecek lagi biocompatibility-nya. Jadi challenge-nya itu pasti entah itu dia memiliki memiliki compatibility yang sama atau jauh lebih buruk dibanding in vitro, itu masih challenge juga. Dan juga penggunaan magnetic nanoparticles itu masih, walaupun secara proof of concept itu tuh dia biocompatible, tapi masih beberapa riset itu masih opposite. Jadi masih bilang bahwa si magnetic nanoparticle itu toxic ke dalam tubuh. Karena ini masih proof of concept ya. Kemudian tracking and navigating. Jadi walaupun udah banyak juga tracking sistemnya ini, tapi tetap dia itu masih misalnya kayak di dalam tubuh banget, itu tuh masih susah buat trackingnya. Kemudian in vivo operation-nya. Dan yang terakhir itu intelligent control. Jadi intelligent control itu lebih ke integrated system. Jadi misalkan microbot ini bisa diarahkan langsung ke automatically bisa dikontrol, itu lebih bagus ya. Jadi kalau kita punya microbot ini punya intelligence yang bagus, itu bisa bagus juga buat diaplikasikan ke depannya. Oke, mungkin saya masih punya waktu berapa menit, Pak? Mungkin kalau ada yang mau bertanya atau
sekitar 2 menit waktu presentasinya lah, sisa.
Jadi saya mau nampilin juga ini tentang promosi lab saya. Mungkin kalau ada yang tertarik bisa hubungi profesor saya. Oke. Ini saya tampilin juga dulu ya.
Everlasting dream for the whole of humankind, the life of good health and longevity. The age of medical science in which such dream is being turned into reality. Everlasting dream for the whole of humankind, the life of good health and longevity. The age of medical science in which such dream is being turned into reality. The most secure, perfect innovation of life sciences. We create, the world recognizes. Humankind in the age of centurions. Owing to the development of medical science and aging phenomenon, the necessity of safe and precise medical robot technology is consistently on the rise. Up to date, thanks to ceaseless efforts and development, Korea's technological competitiveness in the field of medical microrobot has come up to a world-class level. With a view to intensively developing such competitiveness into specialized strategic industries, selected for Medical Micro-Robot Center Construction Project. As a part of the government's Industrial Technology Infrastructure Development Project in 2016, Gwangju Metropolitan City and Robot Research Initiative at Cheonnam National University opened Medical Micro-Robot Center as the country's first, making a way for a new future of the medical micro-robot industry. Playing a core role in Medical Micro-Robot Center, Robot Research Initiative has created extraordinary achievements such as, in 2001, development of the world's first colonoscope robot. In 2003, development of capsule endoscope. In 2010, development of intravascular therapeutic microrobot. In 2013, development of bacteria nanorobot. In 2016, development of macrophage-based biomedical microrobot. In 2017, the world's first development of stem cell-based biomedical microrobot, taking a place at the cutting edge of innovation of biomedical micro-nanorobot research through active technology transfer in partnership with a variety of companies. Toward accurate diagnosis and treatment of human body diseases, we here at Medical Microrobot Center presented a new paradigm for medical microrobots by developing the nanoscale bacteria-based medical nanorobot, and have been acknowledged for our technological power as we successfully performed the world's first experiment on animals using the microscale intravascular therapeutic microrobot, along with cardiovascular interventional procedure enabled by active steering controlling technology of the milliscale robotic catheter system. Moreover, we've developed higher value-added surgical robots, such as image-guided brain surgery robot and robotic bed system for heavy ion therapy, which led to precision surgery with the highest level of stability. We here at Medical Microrobot Center, let alone for medical field, toward applications in industrial robots field, gave birth to advanced concept cable robots. Even today, making a persistent commitment to performing R&D, enough to play a critical role in the industrial field. Located in the Gwangju Special R&D Zone, Medical Microrobot Center serves as a regional hub for supporting businesses by integrating state-of-the-art micro-nano research equipment for joint activities of research with related companies. Also, with testbed facilities such as Small Animal Research Lab, Cell Culture Lab, and Micro-Nano Robot Prototyping Lab, MEMS Fab Cleanroom, X-ray Shield Cabin, etc. MRC prides itself on its own research facilities of the world's highest level as a standalone research facility in the field of medical microrobot.
Mungkin cukup lah ya. Oke, mungkin kalau ada yang bertanya, kayaknya untuk video promosinya bisa dicek lagi di YouTube.
Ya, jadi hari ini sudah di-record di Zoom, lalu juga ada live streaming, tapi mohon maaf live streaming ternyata tadi telat mengaktifkan, jadi Bobby udah mulai live streamingnya baru belakangan, tapi nanti diupload di YouTube-nya jurusan record dari Zoom-nya, gitu. Untuk supaya full ya, seperti itu. Nah, ini ada satu pertanyaan dari Andiniwati. Untuk mikrorobot diharapkan dapat membantu mengobati penyakit yang kronis. Kelebihan dan kekurangan dari teknologi pengobatan yang sudah ada seperti apa ya?
Salah satu penyakit kronis itu kita bisa sebut sebagai cancer lah ya. Jadi mungkin saya sebutkan tadi adalah, saya kasih contoh adalah macrophage-nya ini, atau ini juga dia difokuskan buat mengobati cancer, breast cancer, dan jadi udah dicek menggunakan breast cancer dan salah satu ada 2 jenis cancer. Mungkin kelebihannya itu dia lebih efektif dibanding misalnya kita pakai kemo, karena kemo itu kan dia lebih ke bagian seluruh tubuh. Tapi dengan menggunakan microrobot ini, dia bisa target cuma di spesifik areanya aja. Jadi spesifik di cancer cell-nya itu. Cuma kekurangannya ini pertama Ini tuh masih proof on concept, jadi belum secara komersialisasi juga sih. Jadi sebenarnya agak susah juga kalau nyebutin kekurangannya ini nih. Gitu.
Oke, terima kasih. Ya, artinya kalau sekilas saya melihat sih dengan nanorobot, paling tidak lokasi tempat penyakit berada itu bisa apa ya? Artinya obat itu bisa langsung ke tempat penyakitnya.
Ya
Gitu.
betul, Pak.
Kalau obat yang konvensional kan dia mungkin harus melalui apa namanya bagian organ-organ yang lain kan, dan bisa jadi itu timbul side effect misalnya ya.
Betul.
Alergi atau apalah mungkin ya, kalau pemahaman saya yang kurang ini. Tapi kalau dengan mikrorobot ini bisa diarahkan langsung ke istilahnya kalau pesawat terbang tuh langsung satu kali jalan gitu,
Oh ya,
nggak
betul, Pak.
transit dulu
Langsung ke
gitu
tujuannya
kan.
aja. Jadi spesifik.
Iya, gitu. Dan juga bisa mengontrol misalnya sequence dari obat gitu kan. Kalau sekarang kan minum obat yang pagi, yang siang, yang malam kan seperti itu ya. Itu kan intinya kan ada sequence di situ ya, ada urut-urutan kali ya.
Iya, Pak.
Nah, mungkin kalau ya Highland kita lah ketika sudah tiba di tempat dengan tadi gaya apa namanya gerakan-gerakan 3 dimensi atau ada puntir segala macam itu bisa sequence pemberian obatnya bisa lebih terkontrol mungkin seperti itu kali Bobby ya.
Betul, Pak. Lebih meningkatkan efektivitas dari obatnya itu. Kalau misalnya
Iya.
buat drug delivery.
Silakan apabila ada pertanyaan yang lain. Mungkin sebelum kita ke pertanyaan, I just want to know, do we have Prof. Paula here? Prof. Paula, are you join with us? So we are waiting her. Nah, mungkin saya bertanya nih Bobby, sebenarnya untuk mikrorobot nih ada berapa gerakan sih? Ada berapa apa ya istilahnya ya, kan ada mungkin gerakan X, sumbu X, Y, Z atau gimana lah gitu.
Kalau sebenarnya gerakannya itu misalnya di magnetik ya, Pak. Saya mungkin lebih spesifik ke magnetiknya aja. Nah, kan kayak magnetik itu dia ada helical. Misalkan dia bentuknya helical microrobot, berarti kan lebih buat motionnya, gerakannya lebih helical kan, untuk mengikuti bentuknya itu. Tapi misalkan dia bentuknya bulat, atau misalnya dia bentuknya kecil banget, dan misalkan bentuknya bulat, itu bisa juga di drag and pulling. Jadi kayak pakai magnet aja langsung ditarik. Jadi cuma ditarik doang. Dan juga ada namanya rolling. Jadi rolling itu dia misalkan bentuknya agak besar dan bentuknya bulat juga. Itu dia kayak muter apa sih? Kayak muter bola aja gitu, Pak. Jadi kayak rolling gitu.
Nah, ya sambil menunggu ya sampai jam 15.01. Kan sudah kebayang ya kalau dari di luar tubuh diinjeksi atau dipakai oral masuk ke dalam tubuh, kemudian ada guidance-nya dengan tadi berbagai macam magnetik, elektromagnetik dan sebagainya, light juga. Nah, ketika sampai itu untuk misalkan drug release ataupun fungsinya yang lain itu kan harus ada stimulusnya tuh.
Iya, Pak.
Nah, misalkan kanker. Nah, bagaimana obat kanker tuh bisa dilepaskan gitu. Sedangkan kan stimulus kalau yang tadi magnetik atau elektromagnetik kan hanya untuk dia bergerak kali ya.
Iya, Pak, betul.
Nah, untuk mendrag rilisnya itu apa yang dilakukan gitu?
Di sini salah satu yang bisa dipakai itu adalah lewat. Ini menggunakan high intensity focus ultrasound. Jadi setelah dia di targeting ke tumor areanya itu, kemudian menggunakan ultrasound ini, dia kayak apa ya, menginisiasi proses detachment proses dari microrobot ini. Jadi ini adalah satu keunggulan dari HIFU ini, dan juga kalau dari hasilnya sendiri, HIFU ini dia efektivitasnya itu sangat tinggi. Jadi setelah 60 detik proses ultrasound, setelah proses HIFU ini, dia hampir 100% rilis dengan waktu 60 detik. Dan selain pakai HIFU juga, itu ada metode menggunakan NIR light, jadi menggunakan NIR kemudian diinjek. Jadi menggunakan, kalau dari NIR ini, dia menggunakan heat. Kalau misalkan microrobot itu dia di expose dengan NIR light, itu panas, itu akan menjadi panas, dan panasnya ini yang akan menginitiate si drug release-nya itu. Atau bisa juga dia pakai natural release. Jadi makanya di sini saya cek juga drug release-nya menggunakan pH 5.5, itu karena buat ngecek si natural release-nya itu. Dan menggunakan natural release juga, setelah 20 hampir 1 hari, itu 50% rilis dari si microrobot. Dan metode lain mungkin kalau metode lain saya agak lupa sih. Cuma yang saya ingat banget itu cuma si HIFU ini dan juga NIR. Ada juga light, tapi saya nggak terlalu paham mekanismenya itu.
Ya, artinya kan untuk microrobot bergerak perlu perlu bantuan dari luar.
Yes.
Kemudian pada saat mau merilis juga dia perlu stimulus kan untuk melepaskan obat misalnya seperti itu ya.
Yes.
Oke, saya rasa sih karena waktu yang membatasi, Bobby, terima kasih banyak atas kesediaannya bergabung dengan kita hari ini.
Ya.
Awalnya saya kira saya kedatangan Korean Idol ya, katanya masih Bobby gitu kan. Jadi gue pengen kayaknya nih rambutnya digunting. Mudah-mudahan cocok gitu kan.
Ya mungkin kalau masih ada yang mau bertanya di kesempatan lain bisa email saya di bobbyadit93@kimera.ra.kr atau 188557@jnu.ac.kr. Terima kasih, Pak.
Oke, terima kasih Bobby. So for your information, we also record this Zoom meeting in first in the Zoom account. We have recorded every time we conduct this online seminar, and then we also have a YouTube channel, so it's live streaming. If you want to see all the series or only this one, you can visit, for example, our YouTube channel. So for the second presenter, I'm happy to present you Professor Paula Peralino. Hello, Professor.
How are you?
I'm fine, Professor. And you? Are you okay?
Very good, thank you. These difficult times, but we are trying to survive.
Aveiro is still cold with the strong wind?
Wind, we always have wind, but not so cold. Now, November, the temperature is very mild, still very mild.
Okay, that's good.
Yeah, for us it's good. Yeah, very good.
So we can start. I will read your short CV. So our presenter is, her name is Paula Maria Lusada Silverina Villarino.
Very good.
From Material and Ceramic Engineering, Universidade de Aveiro in Portugal. So his education background, he graduate from Ceramic and Glass Engineering from the same university, and then got her PhD also from the same department, the same university, for the field of relaxor ferroelectric materials. And now he worked at CISECO, Center for Research in Ceramics and Composite Materials. She is the leader of the electroceramic group within CISECO, and then president of the Portuguese Society of Materials, SPM. Do you still become the president, or?
Not yet, not anymore.
Oh,
Passed. Not anymore, passed to someone else.
And how about the coordinator of the program within the University of Texas?
Yes.
Austin? Still, or?
Not anymore, passed also.
Okay. Okay, so
yeah,
I think
I will send you my updated CV. Okay, so how long do I have?
It's a 45 minutes presentation, and 15 minutes for question and answer. Yes.
Yeah. Okay. So I will share my screen.
Yeah, of course.
So this is my screen. I think you are seeing my screen now, right?
Yeah, but not in the. It's not a full screen.
I know. Yeah. I know. I think now
so it's okay now.
Yeah, so now I think so. So thank you very much, Aditya, for the invitation. I think it's a pleasure to be talking to people so far away in a country that I maybe you don't know, but I know quite well your country. I'm not sure that so many people, at least in Portugal, have traveled in so far remote places. So I have the best memories of the parts of Indonesia that I know, but there's still a lot of to know. So it's really indeed a pleasure to use these difficult times to be online with you and some other colleagues and students. So I will go to my talk in particular, and then if I have time by the end, then I will present a little bit of the university, what we are doing, the group, etc. So I would like to start with to introduce my topic with a short video that I hope that everybody is seeing now.
I'm Frey, the smart city AI of Dubai. In our city, no one owns cars, but rather requests one whenever they need it. Being fully autonomous, these vehicles enable many improvements to daily life, including en route meetings that make the most of every journey. I use location intelligence and sophisticated algorithms to create one connected network that makes travel inside the city and to all over the world efficient and seamless. I also help facilitate on-demand logistics networks, routing deliveries precisely to every citizen's location, even if they're on the move. It's a highly efficient system that incorporates disparate sources of data from drones, cars, roads, trucks, and the hyperloop into a complete and up-to-date network.
Okay, so I think if you see the movie, and the movie is a kind of a inspiration of what is going to be the future of the cities, I think that we heard a couple of words that I would like to use to connect to my talk. So I think we have used this artificial intelligence. That's something that is quite important and relevant, at least in Europe. And I think also in the US, smart city, fully autonomous, data, connectivity, sophisticated algorithms, network, efficiency. So I think these are the words that this autonomous city, this futuristic city, this is an example of Dubai. But if you Google, you will find a lot of examples of what was going to be the cities of the future and how they will be connected. So my talk, it's not exactly about smart cities, but it's somehow related with materials and systems that are that enable this connectivity and this intelligent network, this future. And a little bit in the continuation of what is happening today, like a Zoom long distance talk to the other part of the world or between two different parts of the world. Okay, so the title of my talk is a little bit general. It's electrical polarization phenomena and the association with advanced nano and microelectronics devices. So I think this is exactly these microelectronic devices that will allow us to have smart cities. So that's my point here. Okay, so as Professor IDT has said, and very well, so I'm Paula Villarinho. I'm coming from the Department of Materials and Ceramics Engineering from the University of Aveiro in Portugal. And I do belong to the electroceramics group. So mainly my research is associated with these materials with, I would say, functional materials. And I also belong to this institute that does the research that is called CISECO Aveiro Materials Institute. Okay, so I divided my talk in these points. I will present you, I just presented you, there's a need. I will give you some information on electrical polarization phenomena, some concepts, because I don't know if the audience is familiar with the topic or not. So in order to introduce then my main message, I will somehow quickly, briefly explain how I feel that nanotechnology is going to be an enabler for all of these needs that we have currently. I will pick up a couple of case studies. Maybe I have picked up too many, let's see. And then by the end, I will conclude. As I said, if I will have time, I will go in and present a little bit of the university. So I think it's very clear that we live in a very smart world. I think that's exactly what we are doing here today is exactly a very good, real example of that. And it is said that in 2025, this means in 5 years, everything, everywhere, every data, everyone will be connected. So this is going to be a completely full connected city in which we will have, you know, materials that will enable this connection. And if we see here, we have houses, we have people, we have cars, and then we have all these systems like sensors. The cars will be smart, the house will be smart, the buildings will be smart, everything will be smart. We will have an internet, we'll have a cloud, everything will be connected. To do this, we need materials that will enable us, like sensors and actuators, and all the materials that support the Internet of Things. That's the reality, okay? So we'll have sensors of position, of motion, of temperature, of humidity, of sound, of, I would say, chemical, the flow, the force, the levels. I think we should call it a sensor decade, you know, sensor times, because if we want objects to talk, if we want objects to think, if we want objects to act based on artificial intelligence, we really need devices that will enable that. So I'm talking about sensors. So this is the reason why the sensor markets, it's going to increase tremendously, because it's not going to be possible to do anything without sensing it or actuating it. So that's exactly the point of my talk. So I'm going to be focused a little bit on materials that are really very good sensors, because sensors are not only sensors to sense the ambient, but there are also sensors that then act, that then they become smart. And I'm talking about piezoelectrics. Okay, so piezoelectrics traditional have been used in many different applications like multi-layer capacitors, positive temperature coefficient sensors, piezoelectric sensors, and tunable microwave devices. And we can find them in many different applications. As we move on, as technology is moving on, then we are not just using piezoelectrics as bulk, but we are using also piezoelectrics as films and micro and nanostructures. And that's exactly where we live here. So flexible electronics, smart electronics, biochips, molecular electronics, nanosensors. I think the previous speaker was talking about something related with biomaterials. So we also think that all of these electronics will go into the body to help us, for example, to grow tissues, So that's what we feel that these materials will enable in the future. In addition, we have something that is very relevant, and I should call the attention to this, is that there are also technology requirements. So for this fully connectivity, we need things in which the size are small, because if the size is big, then it's heavy. So, but then we also need systems that will be highly functional. So people is going to say that there will be no more blind people because we will have a completely full artificial vision. So and this needs to be functional. And then it needs to be flexible in the sense that if we want to wear these electronics, they have to be flexible. But on the top of that, we have this problem of sustainability of the world. I think everybody is really understanding that this COVID-19 situation really make the world more cleaner because we stop moving, and because we have stopped moving, then the world become cleaner. So we have a problem of waste. Everybody has a problem of waste, and we are really entering in something that we call, at least in Europe, we call circular economy. This means what? This means that we will use materials, we'll design, we'll produce, we'll distribute, we'll consume, we'll use, we'll reuse, we'll repair, we'll collect, we'll recycle, and then we will make them raw materials again, and the cycle will be here forever and ever and ever. And this is called circular economy. This will diminish tremendously the residual waste. So as I was saying, besides the technical requirements, we have something that is also very important, that is called the sustainability, that is called circular economy. In Europe, we have a new program called Green Deal, and Green Deal is telling us that by 2050, there will be no CO2 emissions. So for us scientists on material science, this is a big, big challenge. So that's my point here. Here again, in this circular economy, I think sensors and actuators will play a key role, okay? So let's talk a little bit about the electrical polarization phenomenon. And the concepts I'm going to present, they are pretty easy. I think everybody in a university has these concepts. I'm just going to remind them to you. If we, I would say, classify materials in terms of conductivity, I think we have, and everybody knows this, we have three main classes. We have the conductors, we have the semiconductors, and we have the insulators. And you can see in this graph that I really like, and the graph that I use with my students, this is conductivity versus temperature. And what you see here is that on the top of the scale, with the highest conductivities, we have the conductors. So that's why they are called conductors, because they have a high conductivity. On the bottom of scale, with the lowest conductivity possible, we have the insulators. And they do not, ideally, theoretically, they should not conduct. So the conductivity should be zero. It's not exactly zero because we don't have perfect materials, as you know, but it's really low. Look to the scale. This is 10 to minus 13 Siemens per meter, up to 10 to 11. So there's a big, big difference between these families of materials. In the middle, as you know, we have a really important family of materials. These are the semiconductors. And these guys, they have a conductivity in between the conductors and the insulators. However, if you look to the temperature dependence, they behave more like insulators than conductors. As you know, in the conductors, as the temperature increases, conductivity will decrease. In insulators, as the temperature increases, the conductivity will increase. And why is this different? Very simple. The mechanism of conduction is very different. In this case, in the case of conductors, we have the electron free mobility. In the case of insulators and semiconductors, we do not talk about the electrons moving. We talk about eventually ions moving. But when we apply an electric field, the insulators will also react. They will not conduct, but they will create dipoles. And that's exactly these dipoles that will allow these materials to be very smart in some applications. So my talk today is indeed about insulators and is indeed about these smart materials. So as I was saying, when we apply an electric field to an insulator material, what is going to happen is that the positive and negative charge of any dipole will be separated. And this creates many different types of polarization, from the atomic polarization, that is a universal phenomenon, valid in all of the materials, to ionic, dipole, and interface. The total polarization of a material will be the summation of all of these local polarizations. And these are the materials that I'm going to talk today. So they are insulators. When we apply an electric field, they polarize. The total polarization that we can measure as a dielectric constant will depend on the frequency of the field and is a summation of all of the process, being the tiniest one and being the one that is common in all the materials, the atomic polarization. Just the, I would say, the distance between the nucleus and the electrons of a material when we apply an electric field. So these are the materials that I'm talking. And within these materials, we have a particular family of materials that we call ferroics. And we call ferroics because they can be ferromagnetic, they can be ferroelectric, they can be ferroelastic, they can be ferrotoroidal. And what they have in common, usually they have in common a phase transition. So there is a temperature in which the system goes from completely disordered, in which we have phenomena associated with a disordered state, to a state in which there is order. And if there is order, it can be lattice strains, electric dipoles, magnetic moments, and this creates materials that are smart. So when we really talking about materials that are smart, these materials that they react to a stimulus. When we applied a stimulus, they react. And usually they react differently from the stimulus. So if I apply an electric field, they can deform. If I apply a mechanical stress, they can create an electric field or a magnetic response or even a lattice strain. So that's why we call them smart. These are the materials that I'm talking today. So if we go deeply in this, and I said to you, I'm just presenting some concepts. So I think in the big family of insulators, we have the dielectrics. Then there is a smaller family, the piezoelectrics, pyroelectrics, and ferroelectrics is some of the most smart materials we have. So what I have here is really a fingerprint of a ferroelectric material that is important because also is a lead-free one. So if we are talking about sustainable materials, this is a really interesting one. And as you can see here, the polarization of the dielectric permittivity as a function of a temperature shows three main regions: a rhombohedral regime, a monoclinic regime, and a tetragonal regime. That these are the structures that are really ruling the properties. And as we move down in the temperature, then the structure changes. This is very, very powerful in terms of properties of materials. So a fingerprint of ferroelectric is really what is represented here. That is the possibility of changing or inverting the polarization of a material. That's something that is relevant. We call these materials smart materials. So how is going nanotechnology to be an enabler? How is going nanotechnology to help us to have smarter materials, smarter devices, smarter systems? So I'm going to give you a couple of examples in terms of nanotechnology and nanophorics. So nanotechnology, and in this case, some ferroelectric materials that I've considered that are relevant. So just to recall, we call the different, I would say, shapes and sizes to nanomaterials like 0D materials, 1D materials, and 2D materials. This is related with the number of dimensions that are below 100 nanometers. So if you find the definition of nano science or nanotechnology, what is said is that this is associated with sizes that are below 100 nanometer by definition, okay, by definition. And this is also associated with materials that change their properties. So we have two things ongoing. Either the size or the size is small, smaller than 100 nanometers by definition, and also they change the properties. And we will see why they change the properties. So if the 3 dimensions of a particle are below 100 nanometer, we say that we have a quantum dot. So it's a 0D material. However, if 2 dimensions are below 100 nanometer, we call it a quantum wire, and we have a lot of wires and fibers. I'm going to show some of the wires we are using. We call them 1D. But if just one dimension is below 100 nanometers, we call it a 2D material. We call it a quantum well. And I'm talking about films, coating, multi-layers. And these are indeed some of the most used currently, I would say, nanotechnology or nanoscience enablers in terms of designing, producing smart materials. So there's a question that pops up. So why the nano stuff changes the behavior? 2 reasons. First, it's a surface effect. As you know, when we decrease the particle size, we increase the surface. We increase the surface energy. The second reason is a quantum confinement. This means that when we decrease the size, the electrons' orbitals start to be confined to some regions in which then the electron moving, it's not the same way. A quantum confinement is very well observed in semiconductor quantum dots. So here I have an example that I like to show that is associated with really what is happening when we decrease the size. And the fraction of the atoms at the surface in nanoparticles is increased when we decrease the size compared with the microparticles. So this means that we have much more atoms in the surface than the ratio between surface and volume. So this means that the surface starts to play a role. And in terms of engineering, this is really very, very relevant. And I think many industries already perceive that. And I'm not going to give you too many examples of the benefits of nanotechnology, but they are already in use for some time. So in terms of quantum confinement, I think, as I said, a very good example is the semiconductor behavior of quantum dots, in which what is happening is that as we decrease the size of the particle, the band gap starts to be larger. And if the band gap starts to be larger, then the color emitted change. So this is a simple example. And why is this happening? This is related with really the confinement of the position of the electron orbitals. And that's the reason why we have a quantum confinement. By the way, this phenomenon was not explained by classical physics. This is phenomena is just explained by quantum physics. You know this, okay? So let's go now to the examples that bring me here today, the examples of nanophorics, just to tell you that I do believe that some of these materials will be relevant in these systems. So my first slide looks like, although this slide looks like a little bit complicated, and maybe indeed it's a little bit complicated. So this is the dielectric permittivity that I mentioned before, that I presented. So this you can read as a synonymous of polarization as a function of temperature. So there's a mess here There are these black curves, and there are these open curves. So what I want to show you here is this is the dielectric permittivity as a function of a temperature behavior of a very famous material, important material in microelectronics, strontium titanate. And what is represented here is the behavior of a single crystal. So if you follow this line, you see that the permittivity is high, and then it goes down, 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 down with the temperature. These are crystals. The highest permittivity is observed for crystals, for single crystals. So then if we prepare ceramics, and the difference between ceramics and single crystals, I'm going to say we have at least we have grain boundaries, then this drops. You see, that's the effect of the grain boundaries. But if we move to films, then the drop is even bigger. So if going back, if really I want to use dimensions below 100 nanometer, I may have a problem. And the problem is that the properties decrease tremendously. And if I do different types of films, then you see these open dots, and open dots, the scale is much lower than the scale on this side. And this is indeed a problem in terms of the properties of these small things. So usually the properties decrease, usually there are much more defects. So what we have really here is a competition between the volume of material, the surface that is ruling, and the probability of having a lot of defects. However, I do feel, and from the engineer point of view, this is clear, where there is a limitation, there is an opportunity. And indeed, we can use these limitations of very small things to make them an opportunity. And that's exactly what I'm going to show to you. The opportunities created by small things in terms of, I would say, electrical responsive materials that might be used for particular systems. Okay, so let's start with 2D ferroics. Let's start with strontium titanate. So what I'm going to show you here is that this material that I said to you, oh, it's really an important material, but when I produce them in thin films, this means around 100 to 200 nanometers, I can engineer the stresses of these materials, okay? So how can I do that? I can do that by depositing a film on a substrate that has a different nature of the film. And that's what is represented here. So what we did was using different types of substrates like magnesium substrate, strontium titanate substrate, lanthanum aluminate substrate, silicon substrate, and aluminum substrate. All of them have a different structure and a thermal expansion coefficient of strontium titanate. And then by the end, after depositing the film, what we get is indeed a different microstructure that is associated with the stress level. So I can induce stresses in my films that are induced by the substrate. This is not happening in a volume. This is just happening in films because the surface is ruling. And also the interface is ruling. So what good properties can I get from here? So if you see here, when I do this on magnesium oxides, this is obviously different microstructure. We have a lot of these dislocations. It looks like this film is quite stressed. It's tensile stressed. Let's see what is happening in terms of the dielectric permittivity. And if you look here, it's very interesting. It's exactly the film that is more tensile, that contains, in this case, more compressive stress. They have a lot of these dislocations. They have the highest permittivity. So I was able to, by simply changing the substrate, to increase drastically the response, the electrical response of my material. I would not be able to do this with a bulk material. So my example here is, okay, when we decrease the size of materials, we face a lot of difficulties. However, when we decrease the size of materials, we can engineer the material to a certain level. And that's what I'm representing here. But this is not only, I don't have time to go into details, but strontium titanate is really an important material in terms of tunability. This means I can tune the dielectric permittivity by using an electric field and by using the temperature. So again, here I can see the highest tunability of my films is associated with the films deposit on magnesium oxide, those that are more compressive. So from that point of view, it's a very interesting example in saying we may have difficulties, but we can use them, we can leverage them. And that's what is exactly represented here. So these are the films on magnesium. You see the microstructure, and here are the highest possible tunability. 60% is a very good value compared with the other films. And here you can also see the dielectric permittivity, that is the maximum. So the message here is we can use the difficulties to leverage advantages. Okay, I'm going to show you another example following this logic, using these materials that are indeed enablers. They are piezoelectric, they are ferroelectric, they can be used in all of these sensors. And the example is in the continuation of what we mentioned here. So this is our material that is a barium scandium lead titanate, and it has this structure. And usually these films, to be used in microelectronics, to be used in circuits, they have to be deposited on platinized silicon substrates. And usually when we deposit a very thin layer, okay, this is up to 500 nanometers, usually this doesn't like the substrate. But if I use a buffer layer, so again, I'm engineering the film by using a buffer layer that is an oxide, then the conversation between my oxide and my bottom electrode layer becomes easier. And that's exactly what I'm representing here. So I was able to orient my film according to the crystallographic orientation of this lanthanum nickelate oxide. And then by the end, the properties of this film are higher, including the ferroelectric hysteretic response that is aged in terms of aging becomes much better. And the hysteresis loop is very clearly represented here. So again, this is another example that is saying, oh, look, we really decrease the properties of our materials when we make them thinner and thinner and thinner, but we can use, I would say, this small thickness to improve. In this case, for example, by using a buffer layer, something like 200 nanometers was enough in this case. Another example is Bismuth White. That's a very good material. It's one of the unique multiferroics, true multiferroics. And here again, what I'm showing here is how a thin film can be deposited on different types of substrates and how this really reacts and forms. As you can see here, the level of stresses is very different. In the case of the lanthanum nickelate oxide, I have a much lower stress level compared with the others. I think this stress level also affects the way the grains grow. And here you can see very columnar grains. So it's not exactly an epitaxial film, but it's something that is really oriented. And the other thing interesting is that if really the stress is high, sometimes the material doesn't like it. So what is happening is that in some situations, the stress is so high that the material is really creating a secondary phases. And that's something we were not expecting. By the way, to see this, we have to use high resolution transmission electron microscopy. So once again, my point here is that we can really engineer the properties. You see here, the microstructure is very different and the dielectric response is really very different. Being this one, it looks like that our films like oxides, they like to talk with oxides. So these are two oxides and we expect a better response. And that's indeed what is happening. So even the phase formation of the film on the top of an oxide is much faster than in the case when I have a metal. So again, The message is when we use the buffer layer, we really engineer the properties of the materials. But we can also use something else that I think is also interesting. We can use nanoporosity. And you may say, so especially if you are coming from a mechanical, I would say, a mechanical background, you will say, oh, we don't want porous materials. Usually porosity is not good for mechanical resistance. And maybe you are right, but porosity might be very helpful. Okay, macroporosity is very well known in everything that is filtration, catalysis, etc. And even in some dielectric materials, we can really improve the dielectric figure of merit if we use figures of merit, if we use really porous materials. And it looks like that we can have tunable photonic band gap materials based on this porosity, because this porosity will somehow interrupt wherever electromagnetic wave will go through the material. And if this porosity is really organized, maybe this interruption will be organized. And everything that is organized in order may create a different behavior. Not talking exactly of artificial materials, but somehow on changing intentionally by designing the material, the final properties. Okay, so that's exactly what we tried to do, was trying to understand in our materials if this nanoporosity would somehow affect the ferroelectric behavior. And it's very interesting what we found out. So the first thing we decided was really to model the porosity. So this is just a suggestion. I think whenever it's possible for you to model the behavior of your material, try to do it. There's a lot of tools now available to everybody that will allow us to make simulations. And making simulations before going to the laboratory, it's really very powerful. So that's what we did here. So using a Monte Carlo simulation, we were trying to understand how porosity is going to interact with my ferroelectric behavior. And what is represented here is just a simulation and the modeling, so it's nothing experimental. So we were increasing the amount of porosity, and we also were increasing the localization and the shape of the porosity. And then switching, trying to switch. So this is polarization, this is electric field, as I mentioned before, this is an hysteretic curve. You can have this for, ferroelectrics and for ferromagnetics. And what was interesting is that what we were observing, depending on the porosity, the switching was being facilitated. And that's quite interesting. We were not expecting that. We were expecting porosity to be really making difficulties in different things, including switching. And that's not what is happening. So what we discovered was, if we have porosity that is smaller than the domain size, this porosity will help the switching of the polarization. And as you can see here, as we increase the porosity, our coercive field, that is exactly the measure that will facilitate us the switching, is really decreasing. This is a theoretical prediction. This was our theoretical result. So what is the reason for this? We were really struggling a little bit, but what we think is that when we have this nanoporosity very well organized, distributed in the lattice, they will really help to create electric field conditions in which the switching is easier. So they will somehow counteract with effective grain boundaries that are pinning the switching. And okay, so we continue doing a little bit more finite element modeling. The first one was Monte Carlo simulation. The second one was finite element modeling. And that's what we were really understanding, is that the model demonstrates that the porous films with vertical pores are much more favorable for local switching than the dense films, due to the high electrical fields. So the high electrical fields is really helping the switching. By the way, this is really interesting because now we are studying a completely different topic, and we are seeing again that locally sometimes the materials feel, they sense more the electric fields than as a global. And these local effects might be very relevant. Okay, so we did experimentation just to prove our theory. So we did different types of materials, lead titanate, barium titanate, multifluorics, and then we also decided to put something inside of the pore. So I'm going to show you. We use this block copolymer preparation. It's chemistry. It's a little bit complicated chemistry, but we were able really to make a very porous, organized structure. And our papers are published. If you have any questions, I will be available to discuss these questions with you. So let me show you some of our microstructure. This is in the case of lead titanate. You can see here, and you can see how they varied with the temperature. Of course, if we anneal them to very high temperature, we will simply destroy the porosity. We make a dense material. But while they are porous, that's what we did. So these are real data. These are not simulations. So what is represented here is nanoporous materials, and here dense films, the same in this case is lead titanate. And what is represented here is atomic force microscopy, piezo force microscopy local, in which we locally measure the switching of the polarization. And what is represented here is that for the porous, again, for the porous materials, it was much easier to switch, and also we were able to switch much longer time. So really the nanoporosity, and when I'm talking about nanoporosity, you can see here, they are really, really small, something like 20 nanometers, sometimes 10 nanometers, sometimes 30 nanometers. They indeed facilitate the switching because locally they create eye fields. So that's the response, again, from atomic force microscopy, because these things are so small that that's the tool that enables us. And as you can see here, the coercivity of, that's something important, is the amount of electric field that I need to use to switch. So this means that the amount I have to use is smaller, and this gives us a better properties for these local nano materials. We verified the model in terms of local materials, and we also verified the same phenomena for this bismuth white. So we decided to produce these nano honeycombs, very well organized, as you can see here, very well organized, and try to see what is happening in terms of response. The same phenomena. So to prove our theory, we used the different types of materials, as I mentioned to you, lead titanate, bismuth white. We observed the same phenomena. For the porous materials, we had a better, easier switching because we create high electric fields around the pores that will help the dipoles to change, the domains to switch, and then just facilitate the switching polarization. Okay. And also we measure the magnetic properties, and we verify that that is also an enhancement of the magnetic response to the porous materials. So again, we prove in a different system that the nanoporosity will really improve the performance of our materials. So the other thing we decided was, okay, so let's fill these small pores with something. And, if you look at the image, it's very easy, but then in practical, to put some small particles within these very small holes, this is much more difficult than playing golf. And maybe those of you that know what golf is not easy, but putting these particles inside of the holes as films, it's like a nightmare. So we use supercritical fluid deposition. We collaborate with a Spanish group. And indeed, as you can see here, we were able to put tiny, tiny nickel particles, nickel metallic particles inside of our films. This was a beautiful work. Okay, we were not able to put one particle. Maybe in some holes we put more than one particle. But our idea was really to prove the concept that besides changing the properties, can we use this nanoporosity to do something useful? And indeed, we prove here you have our films, and then films with the nanoparticles inside. And again, the properties of these materials improved. We're able to switch them and also to change the magnetic behavior of this composite from an antiferromagnetic to a diamagnetic material, and this might be useful in some applications. Okay, so I think this is the last example. I think I still have some minutes to go. I would like to talk a little bit about carbon nanotubes and how carbon nanotubes is. I think this is the last example in terms of that I found for today, in terms of nanotechnology to enable, as an enabler to advanced materials and materials that should be used for electronics and things like that. So situation here is that we are decreasing the size of the electronic circuits, and that's what is said here. This gate length, this is called the gate length in the electronics industry, is really decreasing, and by 2022 it's going to be 4 nanometers. That's extremely difficult to really use or fabricate this gate length of 2 nanometers. The materials start to communicate, and then the performance is not good. So in terms of ferroelectric materials, the idea here was using carbon nanotubes and to coat them, and then to construct structure that will be on the pillar base to improve the signal and sensing capacities of things. But of course, we have a problem when using carbon nanotubes. Is the carbon nanotubes, they decompose. So the first thing we did was really trying to see the thermal behavior of our carbon nanotubes, just to be able to understand if we can coat them with an oxide and then doing a thermal treatment to this oxide. And what we observe is that if we deal with carbon nanotubes in a reducing atmosphere, they will keep very carbon nanotubes until a very high temperature. I think that's a very nice result. We have this publication here. This has been quite well cited, in which we really present the behavior and the different atmospheres with the different conditions in which we can keep the carbon nanotubes intact as much as we can. And that's a relevant result. So then what we did was really covering our carbon nanotubes with different types of materials like lead zirconate titanate and also barium titanate, and then treat them and then measure the properties. And this was quite interesting. As you can see here, we have different, here is the structure of our carbon nanotube, and then we have something on the top. And then what we are measuring is indeed properties that were not able to be measured before. And this is not easy, I would say, covering the tubes exactly what we want and how we want. It's not an easy task, but I think it's feasible. Here you can see the different types of carbon nanotubes coated with different materials. In this case, the barium titanate with a very nice ferroelectric response to this material. We are now publishing all of this work. I hope this will be available soon. Just to finalize, I also said that these materials should be flexible because if we want to use them in different conditions, they really should be flexible. Making flexible electronics, as you know, it's not easy. And the reason is because materials that are flexible usually are polymers. Polymers degrade easily, and they are not very compatible with oxides. So we have to find a way here of making them compatible with oxides. So applications for flexible electronics are enormous, as you know, enormous. And we have a lot of companies now in Portugal interested in flexible electronics because this can be a commodity sooner or later. But the challenge is, if we want to make them really compatible with oxides, it's low temperature processing, still a very high challenge of processing materials. Okay, as you can see here, the maximum temperature that still can sustain is 900 degrees C without anything happening. However, if you use polyester at 120 degrees C, it's the maximum temperature you can use polyester. So it's very difficult to make a composite of steel and polyester. This is almost impossible. Or it's very difficult to deposit an oxide on the top of polyester if you need a treatment to that oxide. That's a challenge. Okay, there are different types of things that we can do to deposit films, as you know: physical vapor deposition, chemical vapor deposition, and epitaxial growth, large areas. These are the things we always want. However, we really need something that really decreases the temperature of the processing of these materials. So we develop a technology in which we somehow are able to decrease considerably the temperature of crystallization of these materials. And the technology is we use some nanoparticles that are produced by hydrothermal method, and then using these nanoparticles inside of our chemical solutions and using UV radiation and then rapid thermal annealing, we are really able to crystallize our films on the top of flexible substrates at a very low temperatures. And that's what is represented here. So in this case is bismuth white oxide nanoparticles, and we prepare them. They are really small, and then we put them in a suspension, and then we heat treat them in a film. And as we can see here, at 300, around 300, we are able to have already our bismuth white oxide. So 300 is already a very low temperature that allows us to use flexible substrates, as you can see here. So we use a Kapton substrate. We put a film on the top using our proprietary development, using some seeds, and using some seeds at 300 degrees C, we already have bismuth white. So we already have an oxide. This is really relevant because this oxide is just formed at very high temperatures, around 600, 700, 750. And this is incompatible with polymer. So here are the answer. Here is the response of the materials that contain seeds and are treated just at 300, very, very low temperature, and we have a ferroelectric response. So I think this is a very nice result that really allow us to put here our bismuth ferrite deposit on polyamide substrates with a very low temperature of crystallization, making them flexible. Okay, so I think I'm reaching the end of my talk, and I think I gave a couple of examples. I sincerely hope that I passed my message. So I think I have time to conclude and to talk just a little bit about my university, if you allow me. So in terms of conclusion, my message today was, I think we really live in a times in which everything is connected. So the smart cities that are predicted for 2030 or for 2040 are really a digital overlay. This means that we have to have structures and systems and sensors and piezoelectric based materials, ferroelectric based materials that will enable these applications. And these applications will be also enabled, from my point of view, using nanotechnology. So we have size requirements, we have functionality requirements, flexibility, but we also have a sustainable planet to take care of using sustainable processes, no doubt on that. And I think that nanotechnology will enable to that. So I give you a couple of examples of the limitations when we go small in size, but also how can we surpass the limitation and also creating other different types of properties when we use nanotechnology, I would say, features. So I presented you a couple of examples, including the examples that we are now developing to make some flexible electronics, making the compatibility to all of the things, using lead-free materials that are sustainable, and trying to use as much as possible sustainable processing, decreasing the temperature of crystallization that's going to decreasing the CO2 emissions and making all of the things more sustainable. So this is really a teamwork. I didn't do this alone. This is a work that has been carried out for a long time. And these are my collaborations everywhere in the world. So United States, UK, and in Portugal, a couple of people, and Italy and Romania, Spain and Ireland and India. And this is, Hungary. This has been a long teamwork. It has been a pleasure to work with these people. Some of my PhD students that are already gone, working in companies, etc. Okay, so thank you very much. Thank you for listening to me. And if I have a little bit of time, I think, Aditya, please tell me if I have maybe 1 or 2 more minutes to talk about my institution. Can I?
Yes, please.
Okay, so this is my country, and I really encourage you to have a look. So this is one of the movies that you can have a look and see my country. It's a very small country, but it is an important nation in Europe. And we are surrounded by the ocean. So it's more or less like you, not so much, but also the ocean is very important in our life. Okay, so I'm coming from the University of Aveiro in Portugal. And you can see a couple of videos of the university and how we work and the campus, etc. And this is the map of the world. And I always like to say, so you are located here, right? And I always like to say, we are in the center of the world, okay? That I like to say this. Now, not exactly like Americans, but if you really look at the map, we are here. This is Portugal. So we are in the center, and we are surrounded by water, and we are the last European country before getting to the Atlantic Ocean. And this is giving us a geopolitical importance. Okay, here we are. This is Europe, as you well know, and this is Portugal. This is capital. So this is the capital of Portugal. As you can see here, our neighbors are the ocean, besides Spain. Okay, so these are the only neighbors we have. So this is the capital. This is Aveiro, where I'm located, and I'm located very close to the ocean, 5 kilometers to the ocean. That's our location. These are some of the images of the city, in which you can see we are surrounded by canals because the ocean goes into the land and gives us these rivers. These are salted rivers, and these are typical images. I think, Aditya, you still remember this. And these are really the salt ponds that we have around. And as you can see here, this is an overview of the city. You can see water everywhere. We are flooded by water. These are the beaches around us. They are not tropical as yours, but they are also beautiful. Lots of waves, a lot of surf. And that's the campus. That's the university. That's my building. And that's the campus and distribution. As you can see, this is water. So as I mentioned to you, it's a nice campus because it's very well concentrated, all located in very close. So it's walking distance campus, this one. And that's different images of the campus that I think is quite beautiful. And all of this building, this is our building. That's the building I'm located in. And the University of Aveiro is really ranked as a very good university in Europe. And one of the very best universities in Portugal. And I would say that in material science is the best one, because CISECO is the biggest associated laboratory on material science. So if you really considered something about materials in Portugal, it should be at our university. And we're ranked in the 2nd place as university in general, okay? So CISECO, as I said to you, is the Institute of Materials. So if you Google CISECO, you will find a lot of things. Now it's currently a very big center for research. We have 3 main lines, and this is going to, the first line is associated with materials for communication technology, where I'm involved. So my research is really involved in this working group. We have materials for energy and industrial application, and of course we have sustainability and biomaterials as well, and different areas of research. So in terms of our research, and here I should say, so when we started, Professor Aditya asked me, are you still the president of the Portuguese Material Society? Are you still the coordinator of the relation with the US? No, these activities have passed, because usually we have terms for that. And in the case of as president of the Portuguese Material Society, I did I did 6 years, and it's really too much of that. But in the first day of January this next year, I will become vice president of this CISECO Institute. Okay, so this is going to be a kind of an important and a new job for me. It's a very challenge because this institute is currently around 450 researchers. So it's something that is really big. Let's see how am I going to do that. And that's a challenge. So in terms of our research, in terms of research of my group, really we are doing, as I think I clearly mentioned, electroceramics, and we are interested in all of the things that are related with sustainability, low cost, temperature. Additive manufacturing is becoming very, very important to functionality to do with our materials. So if I have to define myself, I would say that my main area of research are going to be these functional materials, electroceramics, dielectric, nonlinear dielectrics, piezoelectric, ferroelectrics. We prepare them by conventional methods, and here they are. And more recently, with non-conventional methods. We are becoming very interested in additive manufacturing. We are becoming very interested in alternative technologies to sinter, like flash sintering, cold sintering. We prepare materials in different forms, bulks, films, nanostructures, porostructures, flexible structures, single crystals. We prepare them for all of these conventional, I would say, technologies that I just presented to you, but we also prepare them for more non-conventional, like we are exploiting them as tissue engineering platforms for bio applications. And we are also very concerned with sustainability and better ways to prepare them, okay? We have now a maker's lab in which we have our printers to print different types of materials. We have now a very big project with a company that wants to embed electronics into cars. And we just started. We are going to organize this microwave materials meeting. This was supposed to take place this last September, but it's now moved to 2021. Sooner we will, because of this COVID, sooner we will start distributing information. So if you are really interested in microwave materials, we are going to organize this meeting in this coming summer 2021, and we expect this COVID situation to be over by that time. We hope so. So if really we considered in visiting the university and studying at the university, or we are all have applications open. We have now currently, this is not 2019, this is 2020. We have an application open for CISECO with PhD grants involved. So if you consider to do a PhD in Europe, you should visit the CISECO website to do that. And there's a lot of information on how you can study in research in Portugal. And I will finish here, and thank you very much for your attention. Thank you very much for your consideration in having me here today and giving me the opportunity to talk a little bit about my science, my research, my university, and my country. Thank you very much, and I'm ready if there is time for any questions you may have. Thank you.
Okay, you're welcome, Professor Paula. Of course, I'm quite sure that the University of Aveiro, especially CISECO, they have a lot of resources like people, facility, finance, so that because I graduated from the European Master in Material Science at Aveiro. So yeah, I motivate all the people here, all my students, maybe not only PhD, for example, master degree at Aveiro, for example. Maybe there are some university scholarship for example, for master or for a PhD degree. And it's pretty sure that for material science and engineering, I believe the quality and the expertise of the people at the University of Aveiro, especially the CISECO. So we just wait for the. Do we have any question to Professor Paula? If you have a question, just unmute your microphone and you can ask directly to Professor Paula. So maybe in the meanwhile we are waiting the question. I will ask you. So it's for me it's very interesting because it's about the functional materials, especially from the electrical properties, I think.
Yes.
And in the multi-layer structure, if you want to make, or if you want to design a multi-layer structure that you saw to us, what is the important aspect to design so that we can control the properties, for example, as you said, with this, you can put without or with buffer, for example, without or with oxide, for example. So what is the design consideration behind this structure?
Okay, thank you, Aditya. Thank you for the question. I think it's an interesting question. So different things we need to consider, of course, different things. So the first thing we usually do is we try to understand the compatibility between these the structures, the layers. So the first thing we try to understand if they have any similarity in terms of crystallographic structure. Okay, so if you have a cubic structure and then on the top of that you want to construct or grow something that is hexagonal, you may have some problems. You see, so one of the things we consider is crystallography of the several layers. The other thing we consider also, particularly if we need to do an heat treatment, we also consider the thermal expansion coefficient. Okay, and these two things, the crystallography, the lattice match, I would say, this is called the lattice match, and the thermal expansion coefficient, the two things will create these stresses. Okay, so theoretically you can predict this. You know the crystallography of your materials, then you know the thermal expansion coefficient, so you know what is going to be the final stress state. If the stress is too high, you may really destroy your film, or not. You may deform your film in a way that is important. So, but the other thing you should consider also when we consider this, when we design these structures, is also the adhesion. Some materials adhere better than others. So if you really want a structure, you have to guarantee that they like each other. There are different ways of avoiding this or overcoming this, if this will be a difficulty. It's exactly depositing a very small nano-sized buffer layer, and there are many. And the other way of considering this is really functionalizing your substrate, for example, or your bottom layer, and functionalizing it chemically. I'm remembering that we are using sealants, a kind of a organic silicon molecule, to deposit on the top of a stainless steel to be able to deposit a polymer on the top, because the polymer doesn't like the steel, and the adherence is very, very small, the adhesion. So what we do, we functionalize chemically. We deposit molecules, and then when the other material comes on the top, it starts talking with these molecules. So it sticks there, stays there. So I think in general, I would consider, to answer to your question, the thermal expansion coefficient, crystallography, and then chemical affinity. I think with these three things, you really can design materials that will be useful for the applications that you are envisaging. I think I have answered you.
Okay, thank you, Prof. Paula. So maybe, especially in our department, it's we are we are metallurgy department.
I know that, yeah.
But we have several courses in material science and engineering, and one of them is functional materials. So it's
Very
a
good.
good chance for me to learn about these functional materials.
Very good, thank you.
And so maybe if you don't mind, you can tell us if, because it's a multi-layer structure, and we applied let's say a voltage, a gradient voltage between two surface, the opposite surface, for example, top and bottom, for example.
Yeah.
So what happened with the, I don't know, with the electron or with the ions, for example?
Yeah. Okay. So I think maybe we go back to one of my favorite images that I use with my students that I like is this one. Okay. Okay, that's the image. So as I was saying, we all know that we have these major classes of materials: conductors, semiconductors, and insulators. Major classes of materials. There is another one that is called superconductors. Okay, and the superconductors really are even above this. However, the theory behind the superconductivity is not yet fully explained. Not yet. Okay. So if we have a conductor in which the conductivity will be very high, when we apply an electric field, what is going to move are electrons. So they will move from one side to the other. They will even move at room temperature very easily. It is called the model of the free electron. It's free to move all over the lattice. And what is happening is that when we increase the temperature, then it looks like that the movement of the electrons decreases. And this is somehow related with the interaction of the electrons moving with the phonons of the lattice, phonons vibration. So as we increase the temperature, the vibration of the lattice increases, and then this affects the movement of electrons. So to answer to Professor Aditya is, in conductors, the species that are moving, the species that are responsible for conductivity are electrons or holes, the absence of an electron, okay? However, when we deal with these insulators, that's not what's going to happen. There are no electrons. By the way, they will supposed to be zero conductors. They were supposed to be perfect insulators, but there are no perfect insulators, as you know. There is nothing perfect. Thanks God, nothing perfect. So there are no perfect insulators. There is always a little bit of conduction. And in this case, the conduction increases with the temperature simply because the temperature increases mobility. And in this case, we don't have free electrons. We have electrons tied to the electron orbitals. They don't move easily unless we apply a very high electric field, and then there's a kind of a collapse of the structure, and we have an avalanche, and the structure is destroyed. The material can be even broken, and then we have a Joule effect associated with this movement, this avalanche of electrons, and then there's a melting. Okay, that's not what happened if we use moderate electric fields. When we use moderate electric fields, what is happening is that we don't have electrons, but we have dipoles. As I mentioned to you, we have atoms with positive and negative charge. And what is going to happen is that there will be a shift of the positive and negative charge according to the electric field. We have this shift at the atomic level, at the ionic level, then at any interface. Whenever you have a positive and a negative charge, there will be this shift, this displacement. No more than a displacement. There is no current. And if there is a current, then usually it's associated with ionic mobility. And as you know, we have ionic conductors, and there's a lot of things ongoing with ionic conductors. And we have a movement of ions, but it's never as high as conductors. So the ionic conductivity is very moderate compared with any of the conductors we have, okay? So it can jump to maybe -3 Siemens per meter, never to 10 to 11 Siemens per meter, okay? So the species that conduct are very different. I will repeat, here electrons and holes. Here, if there is ions, and what is happening here is mainly displacement. Did I answer to you, Aditya?
Yes, yes. Thank you, Prof.
Thank you very much.
Okay, so as I told you at the beginning, we have a YouTube channel, and we
Okay.
record this Zoom meeting.
Okay.
And I hope our students, our colleagues, and all the people around the world, because I promote this event by online media, and I think not the Indonesian people know this event, but also many people. For example, if I saw that people register from India, from Nigeria, for example, but I hope that one or some of the people will contact you.
Yes,
to ask anything about this electroceramics, and I also for sure that in the future I will contact you again for any kind of reason. I'm not sure right now, but I will contact you.
Very good. So Aditya, I should also say that we are always looking for people that wants to come to do Marie Curie training. And Marie Curie training is a very prestigious system that Europe is financing people, mainly people with already PhD. So we are always looking for excellent people because ideas we have, facilities we have, and we like to have foreigners with us because this brings the diversity that we need. And internationalization is extremely important.
Yes.
I think this was a great idea. So I congratulate you for what you are doing. It's really impressive. You are having very good speakers, very highly recognized scientists in the world. So thank you very much for involving me. It was a pleasure to do this.
You're welcome, Professor.
Thank you very much.
And my regard to all the people that I know
at very much.
ceramics, and also Professor Anna Barros.
Yes, I will say this to her.
He will speak with me at the beginning of
yes. She was the responsible at that time. Yes. Thank you very much. It was very nice to talk and see you. This is a great opportunity. So that's the good thing of being confined.
Yes.
It's not only bad things, but it's too bad, but there is a little bit of good things, and this is one of them. Thank you very much.
The positive effect of this COVID-19.
Yes, absolutely. Thank you very much. This was indeed a pleasure.
Thank you.
Thank you very much. Thank
Professor
you.
Paula, see you again in the future.
Thank you very much. Thank you. It was very nice.
So all the participants, please fill this the Google form in the chat room. Later we will send you the e-certificate, and I hope Professor Paula and Mr. Bobby, they don't mind to share their slide to the participants. I don't know if you don't mind, of course.
Yeah, no problem. For me, no problem. I will send you a link to the slides. Okay.
So,
thank you very much. Thank you. Bye. Thank you.
Bye.
Bye. Thank you.
Untuk para peserta, para partisipan, saya tunggu sampai 4:30 ya. Kemudian lebih dari 4:30 Zoom meeting ini akan ditutup. Jadi segera mengisi Google Form untuk memperoleh e-certificate dan PowerPoint dari pembicara. Terima kasih. Wassalamualaikum warahmatullahi wabarakatuh. Selamat sore.